Hello everyone, and thanks for watching Edupedia World videos. We now go back to the very basics of quantum mechanics and try to put it into the new language of linear algebra because that is what the mathematical formalism of quantum mechanics looks like. So the things we've learned till now were the certain conditions, whatever satisfied those conditions were termed vectors. And then we had the concept of linear transformation, which changed a vector from one thing to another. So you could transform a vector from one to another, and as long as it satisfied the linearity condition, it was what was called a linear transformation. So this was the mathematics. Now in quantum mechanics, we've seen a few problems up to now, such as the infinite square wheel, the harmonic oscillator, and we end up solving for the wave function. And I'll just show these things in a second, but the wave function satisfies all the conditions that are needed to qualify them as vectors. So the wave functions, and remember I said in the very first video, a wave function is basically the state of a particle. It is everything that is possible to know about the particle or the wave that there is to know. So the wave functions satisfy conditions for vectors, and when you measure something, you change one wave function in one state to another. You basically transform that, and those transformations are what are represented as observables. So we have wave functions which we find using the Schrodinger equation. The wave function will be similar to what is mathematically called vectors, and you will have observables such as momentum, position, kinetic energy, and they will be basically linear transformations on the vectors, changing the wave function from one state to another. But there's one small difference between wave functions in quantum mechanics and vectors which we've seen up till now. That is that wave functions generally are infinite dimensional. We saw in the video of linear algebra what a dimension of a vector is, and it is basically the minimum number of bases required to independently specify it. But wave functions have infinite dimensions. They are not 3 dimensions or 4 dimensions or 5 dimensional finite dimensional vectors. In fact, they are infinite dimensional, and so there are a few differences in the definitions which we've seen till now. The first is, normally when you had a vector, it was represented like this, alpha, and after you've decided a basis, it corresponded to an n tuple of components which gave it a basis. So for example, it might be a1, a2 till an. So these n numbers a1 to an decided alpha for an n-dimensional wave. Also, when we talked about the inner product, let's say we had alpha inner product with beta. The definition of that was a1 star b1 plus a2 star b2, where beta is b1, b2 and so on, plus dot 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 plus a1 star bn. And finally, whenever you had a linear transformation, for example, let's say beta was a transformation t times alpha, then this could be represented by a matrix equation. So beta would be b1, b2, bn is equal to, here you would have alpha, which is a1, a2 till an, and this would be a matrix, a finite dimensional matrix, t11, t12 and so on. But in this case, for wave functions in quantum mechanics, when we talk about infinite dimensions, there are some differences to these definitions. First, a wave of a function is not represented by an n tuple, it is basically represented by infinite numbers. But another way of saying that it is represented by infinite numbers is saying that it is a function. So the basic definition of function is f of x, and this is a mapping to y. So for example, every value of x gives you a value of y, and whenever x is between any range, it has an infinite number of values. So there are an infinite number of values y corresponding to one each value of x. So this is the sense in which a function can be thought of as an infinite dimensional wave function, an infinite dimensional vector. And so y is equal to fx, and this is the form in which we found out wave functions in infinite square wave and harmonic oscillator. So f of x, a function, determined between minus infinity and infinity is basically what a wave function is. It is not a finite dimensional vector, but infinite dimensional. But there is also one extra condition which needs to be imposed so that it represents a real particle or a real wave, and that is, we've seen this before, the wave function must be square integrable. Let's say the wave we are talking about is psi of x. Then the integral from minus infinity to infinity of mod psi squared dx, which is basically psi star into psi, this should be equal to 1. Right. Essentially, this should be a finite value, but if this is a finite value, you can always multiply it by a constant to make it equal to 1. Right, that would be the normalization constant. So any wave function which is square integrable is itself a family of vectors. Now you can do this yourself. We had some certain conditions which needed to be satisfied for vectors. Every function satisfies those conditions, but not only that, every square integrable function also satisfies those conditions. So wave functions basically are square integrable functions defined from minus infinity to infinity, and that is what is referred to as the Hilbert space. So for every set of vectors there corresponded a vector space, and the Hilbert space is the space of functions which are square integrable. That is the definition of Hilbert space. It is quite important in mathematics and physics, so it's given a special name. But every single function in quantum mechanics does not live in all of vector space, all of function space. It lives in a subset that in which the functions must be square integrable, and that is called the Hilbert space. So what are the new definitions in this case? First, let's look at alpha beta, or in this case let's look at f. Now we're talking about functions. So functions we generally use f and g. Finite dimensional vectors we use Greek letters alpha and beta. So the definition of this, it was initially a1 star b1 plus a2 star b2 till an star bn, but now you have to integrate it, and the integral of f of x star g of x dx. This is the new definition of inner product, and you can see that what we've basically done is generalize that sum to an integral, because earlier they were finite numbers, now there are an infinite number of terms. Also with this we can define the inner product of a function with itself, f, and that turns out to be mod of fx whole squared dx, because it is fx star into fx, so mod of fx whole square dx. Now there are a few other definitions in regards to wave functions which live in Hilbert space, and these are similar to the definitions we've seen for vectors. A function is said to be normalized when its inner product with itself is 1. So that means f with f is equal to 1. The initial definition which we saw in the very beginning of quantum mechanics was that integral f of x whole square dx is 1. But now we've defined the inner product to be this thing, so now we can redefine normalized to be a function whose inner product with itself is 1. Similarly, two functions are said to be orthogonal if the first definition was integral fx star gx dx is equal to 0. By the way, the limits of these integrals are minus infinity to infinity, or if there is some specific case, for example in the infinite square well, everything else would be 0, so within that well itself. So the limits are depending on the problem, but generally they're supposed to be from minus infinity to infinity. And this basically can now be written as the inner product of f with g is 0. So now we see we're putting everything we've learned before into more elegant definition. Instead of saying that the integral of the complex conjugate of one function multiplied by another should be 0, we simply say that the inner product is 0. Also, a set of functions is said to be orthonormal if every function in that set is normalized and every pair of functions is orthogonal, which means it is a set such that fm, fn, where these are two functions in that set, is equal to delta mn, where delta is the Kronecker delta symbol. So that means if m is equal to n, this is equal to 1. If m is not equal to n, this is equal to 0. And finally, a set of functions is said to be complete if you can represent every other function in the space as a linear combination of these sets. So if every function f of x can be written as summation n is equal to 1 to infinity cn fn of x, you have a set of fn of x such that for every single function f of x you can write it like this, then this set of functions is said to be complete. Right. So this is what we've seen wave functions to be. Now the next step is to see what observables are. And I'll just tell you right now, in quantum mechanics, observables, sometimes they're also referred to as measurables. They are things that you measure in an experiment, such as position, momentum, kinetic energy, angular momentum. And observables are represented by Hermitian operators, not just operators. So we've seen already what a Hermitian operator is. If you have an operator Q, a Hermitian operator is one such that Q dagger is equal to Q. It's transposition and conjugate. And so we already know the property that integral of alpha t beta is equal to t dagger alpha times beta. This is true for any function. But in this case, if it's q, q dagger is equal to q, or t dagger is equal to t, so which gives us t alpha with beta. So the Hermitian operator is an operator such that when you take an inner product, it doesn't matter whether you apply it on the first operator or on the second operator, it gives you the same result. Now we know other properties of Hermitian operators. One of them is that the Hermitian operators has eigenvalues which are real. And if you looked at the expectation value of Q, what was the definition of that? It was integral psi star Q psi dx, which is basically the inner product of psi with Q times psi. Right, but we know that the measured value, the average value of something, whether it's kinetic energy, potential energy, angular momentum, linear momentum, it has to be a real number. Whatever we measure in an experiment has to be a real number. It cannot be complex. So that means we have Q star equal to Q, which basically tells us once again that here you could have Q or Q star, it would be the same thing. And if you have Q star, that would be Q psi inner product with psi. So this basically means the inner product of psi implies inner product of psi with Q psi is equal to the inner product of Q psi with psi. But we already proved a minute ago that this is basically the definition for a Hermitian operator. So we see that in quantum mechanics, everything that is an observable is represented not just by operators, but by operators which have this special value that they're Hermitian. And you can check for yourself, position, momentum, kinetic energy, all of those operators will have this property and they will be Hermitian. Now let's look at what we've seen before in quantum mechanics as being called determinate states. So for example, if a particle is in some complicated state and you measure the position, you are not guaranteed to have a particular value. You will have a probability that it is found at a particular point, some other probability that it is found at some other point, and so on. So that means the current state of the particle is not a determinate state of position. You do not have a determinate value of position. Similarly, if you have a particle in such a state that if you measure the energy, you get 50% probability that it has one value and 50% probability that it has another value, then you do not really have a determinate state of energy. The wave function of that is not an eigenfunction of the energy operator. So let's look at when we do have a determinate state. When we have a particle in a state such that the average value Q of the measurement of an observable gives you the same value, small q, every time. This also means that the standard deviation or the variance sigma squared would be 0. But what is that equal to? It is the average of Q minus Q whole squared. And that can be written as psi with Q minus Q whole squared. Now remember, capital Q is an operator, often it's written with a hat on top of it, and small q is a number. It's the average measured value of this operator Q times psi. But this, with a clever little trick, 1 q minus q we can take to the left hand side, and this will come out to be q minus q psi with q minus q psi. But these are the same thing. So if f of f, we already seen this property before, if f of f is 0, the inner product, that means f is identically 0 everywhere, which means q minus q psi is equal to 0, which means q psi is equal to q psi. And you should already see what this equation is. It is, we've seen before, an eigenvalue equation. And this was a determinate state of q. So if we have a function capital Q which has a wave function in a determinate state, and every measured value gives you the value small q, then this statement would be true, meaning that for psi would be the eigenfunction of this operator q, and q would be the eigenvalue. And we've already seen in a couple of cases how to calculate the eigenvector and the eigenvalue. And now what we'll do is, in the later video, we'll measure the eigenvalues and eigenfunctions for both the position operator and the momentum operator, because they will be quite important. But before that, there are a couple of definitions. Also, this basically tells us, I'll just write it down, determinate states are eigenfunctions of the operator, let's say Q. So now, if you have a particle in a state such that the measurement of energy is guaranteed to give you a particular value, it is in a determinate state of energy, then the state will be an eigenfunction of the energy operator, and the measured value will be the eigenvalue with the particular eigenfunction of that energy operator. Right. Also, one thing I'd like to mention, psi has to be non-zero, but q can be 0. There's nothing wrong with 0 as an eigenvalue, but of course as an eigenfunction, if psi was 0, then this was 0 on both sides. That is a trivial equation which we are not concerned with. But other than that, q can be 0, and there's nothing wrong with the non-zero eigenvector or eigenfunction having a 0 eigenvalue. The collection of all of the eigenvalues of a operator is said to be the spectrum. And if two or more linearly independent eigenfunctions, linearly independent because if psi is an eigenfunction, a psi will also be an eigenfunction where a is a number, and these two are not linearly independent. So if a case is such that, this will be of importance later on, that two eigenfunctions exist with the same eigenvalue and the eigenfunctions are linearly independent, in that case the spectrum is said to be degenerate. So degenerate means you have two linearly independent eigenfunctions which have the same eigenvalue. And that would be a special case we'll see in the hydrogen atom of particular values of energy. Also, we've already seen for a Hermitian operator, we have two results which we've proved earlier. The eigenvalues of a Hermitian operator are real. Eigenvalues. And this is the fundamental reason why you have an observable being represented by a Hermitian operator, because observables have to give you values which are real. And we just saw a few moments ago that calculating the measurement of an observable as an observed value is basically the eigenfunction equation for that operator. I'll not prove it in the context of quantum mechanics. We've already seen from the mathematical point of view in linear algebra why this is true. And the other is eigenfunctions belonging to distinct eigenvalues, and this is basically, we've proved this from the mathematical context, but this is proof of something which I told you earlier, that for example in the case of an infinite square well, you got a function states, one was a sine state, then a cos state, then a sine state, and they were all mutually orthogonal. And the reason they were all mutually orthogonal, it was sure to be that way, was because the energy operator was a Hermitian operator, and if you have different eigenvalues, different values of energy, then the eigenfunctions had to be orthogonal. Now this is not only true for the infinite square well, this will be true for every single case whenever you measure energy, because energy, just like any other observable, is a Hermitian operator. In the next video, we'll solve two equations for eigenvalue and eigenfunction, and those equations will be for the two main operators which we will study most often, the position operator and the momentum operator. Thank you.